Thanks very much, Greg. It took a few more disasters like that to truly set me on the path to theoretical physics, but that was one of the high points. So since Greg brought up Rhode Island's size complex, I can't help but also point out that Rhode Island actually has the longest title of any of the 50 states, because the official title of Rhode Island is the state of Rhode Island and the Providence Plantations. So there. Okay, so yeah, I have this rather strange title. We don't usually see the words quantum physics and global warming together. And indeed, it's true that my physics colleagues and climate science colleagues also are somewhat perplexed by this combination. But I hope by the end of the talk tonight, you'll have understanding of the deep connection between these two areas of science. And I'm going to mention three actually, there's more than three, but I'll talk about three. And we'll gain, hopefully, some understanding of climate from this understanding of this connection. So I'm going to begin in a somewhat unlikely place, Yosemite Valley. I had the great fortune last summer of taking a month off after turning 50 and hiking the John Muir Trail, which is a 220-mile trail. It starts from Yosemite Valley and ends up on the top of Mount Whitney. And it was a wonderful experience. So why do I mention this? So here's the trail coming from Yosemite and going down the backbone of the Sierras and exiting at Mount Whitney. The trail passes one glacier that's visible. Actually, it passes many glaciers, but only one is really visible from the trail. And that's the Lyell Glacier, which descends from the highest point in Yosemite Park, Mount Lyell. And this is a picture of it in 1883. And it was a vigorous glacier back then. And this is what it looks like today. It's no longer a glacier. It's just a patch of snow. And it's ceased to flow. It ceased to have the characteristics of a glacier. And we put these two together. We can see pretty much the same point of view from the camera here. And we can see how much it has receded. Glaciers, of course, around the world, many of them, most of them, have been shrinking, and this one's now dead. So, of course, it raises the question, did we kill it through climate change? And now I'm not going to provide a direct answer to that question, which turns out to be somewhat complicated, but I'd like to give you some framework for thinking about such questions. And so let me begin, since I was talking about John Muir, with a famous quote by John Muir. When we try to pick out anything by itself, we find it hitched to everything else in the universe. And that, I hope, is going to be kind of a theme for the talk today. And there's a picture of the young John Muir. We'll come back to him in a little bit. So I'm going to switch now and tell you a story about quantum mechanics. And then we're going to bring this together with climate. And so the way I'm going to approach this is the way that Richard Feynman liked to discuss quantum mechanics. I was very fortunate when I was an undergrad at Caltech to take some classes from Feynman. And so he liked to emphasize the dichotomy of the world between particles and waves. And so he imagined the following thought experiment where we would have say a plate of metal with two holes in it and maybe a gun or something spewing out particles, little balls of something, ball bearings. And the particles could pass through either this slit or this slit, and they'd end up maybe in a sand trap, and we could collect them. Maybe we'd send 1,000 particles through this barrier and then collect them over here. And if we closed this hole, then the particles would all go through this hole one in order to get over here. And they'd end up, most of them would be over here, maybe a few would ricochet and end up over here, but mainly they'd end up here because they'd be going through that hole. And we could open up two and close one, And most of them would end up over on this side of the backstop, and that's represented by this line P2. And if we open them both, then we get the sum of these two. And so the bullets or the BBs, whatever, the ball bearings, they'd mainly be concentrated in this central region here, but there'd be a little bit over there. And another thing about the ball bearings or the marbles is they all come in discrete bunches. There's 1, 2. You definitely know when one passes through. So this, in fact, this figure comes from the Feynman lectures on physics. So let me contrast that with waves, water waves, for instance. So waves are very different. There's no sense of them coming in lumps. They're just ripples instead. And the ripples could be either strong or faint, but they're continuous. And so you imagine dropping a rock in a pond, for instance, and fronts of waves would pass out from that point. And we could do the same experiment, have those waves impinge on this barrier. Then maybe this is a barrier to a harbor. So this could be a harbor back here. So we only allow the ships to go through these 2 holes. So we protect the water back here from the strong waves from ocean storms. So if we close hole number 2 again and just leave hole number 1, then we'll get some circular waves coming from this point, and they'll emanate out here. And the intensity of those waves will look something like this, much like the intensity of the probability that we found the particles going through slit 1. If we close 1 and open 2, then the waves will emanate from this opening, and they'll hit this absorber, and there'll be places where the waves are stronger, and then farther away from the hole, they'll be weaker. And so the strength of the waves might look something like this. So again, very much like the particle picture. But the surprise is when we leave both of them open, we get a much wilder pattern like this, with a very strong wave intensity right here in the midpoint, the midline separating those 2 holes, because the waves, right along this point, you can see that the crest of waves coming from hole 1 meet the crests of the waves from hole 2, and so they add together. If we go a little bit off, then the crest of one wave is at the trough in between the 2 crests of the other wave, and we get a cancellation. And so the intensity of the waves are small there. So this is called an interference pattern. And let's see an example of this, an actual movie. So here's a movie of water waves. We're looking down on a shallow tank of water, and the waves are being produced by a bar that's just oscillating the water. And here's our barrier, and there's 2 holes there. And you can see this frozen snapshot of the waves coming through. Let's let the movie play. So here are the waves coming in, and they're hitting these points, and it'll play a little bit more slowly now. So now we can see these fronts coming out, and then along these lines here, we see that the waves have been canceled out. This is where the crests meet the troughs. And in the midpoint, the crests add together, and so we have stronger waves. So we have this pattern of waves, no waves, waves, no waves, waves, very different than the particles. So what about particles? Let's go down to the quantum world. Let's look at small particles. In this case, let's look at photons. In Feynman's day, they couldn't really do this experiment. But now we have some very sensitive imaging apparatus, and so we actually do this demonstration for our freshman physics concentrators at Brown. So what we're looking at is light from a laser that has gone through 2 slits, and we see an interference pattern showing the wave-like nature of light. But we also see something else, and that is there's some speckly appearance to this, and let's let this movie go. So you see some sort of speckling, and what we're going to do now is turn down the intensity of the light. We're going to make the light dimmer and dimmer, in fact, so dim that a human eye wouldn't be able to see it. So it's getting dimmer now. And now it's just a collection of points, little flicks of light. Each one is a particle. We're seeing here now the particle nature of light, photons. So just as ordinary matter is made out of atoms, if we look closely enough, we'd see that this solid wood is composed of individual atoms. Light is composed of individual particles. And if we make it dim enough so that we see just a few of them at a time, then they just come apparently at random. And now let's instruct the computer to take a time exposure of those photons coming in, those particles of light. And I'll speed it up a little bit. And now we see the interference pattern again. So here, for the first time, we see simultaneously the wave-like nature of light and the particle-like wave nature of light. Right? It's really a striking demonstration that these particles don't behave like things that we encounter in the everyday world. And why should they? Because we never see individual photons. The human eye is about 10 times too insensitive to see those individual photons. And we see that what we interpreted in terms of waves as the intensity of wave is now really the probability to find a photon. And so, for instance, here, the photons are very likely to be found. And in between, where we have the destructive interference, they're not likely to be found. So if we have a little switch in our interpretation from intensity to probability, then we can reconcile these two pictures. Okay, so is a photon, or an electron for that matter, any particle, is it really a particle, or is it a wave? Is it both? Is it neither? As Feynman would like to say, it's like nothing you've ever seen before, because it's not in our everyday experience. We don't have any intuition for such things. They have both natures, but maybe they have neither nature. Maybe it's not really correct to say they're both a wave and a particle. It's not really correct to say they're neither. They just behave in their own inimicable way, as Feynman would say. And that idea is expressed by an equation, E equals hf. This is another Einstein equation, like E equals mc squared. But I think it deserves to be better known than E equals mc squared because it's actually a much more profound equation than E equals mc squared. So let me explain it a little bit to you. E is the energy of our particle, a photon, a particle of light. So they have a definite energy. That's why the computer can record them. F is the frequency of the light. And so red light has a lower frequency than blue light, for instance. Radio waves are a form of light. They have a very low frequency compared to optical light, visible light. So this equation relates the particle-like nature on the left-hand side to the wave-like nature. And the relationship is maintained to this constant that was first discovered by a German physicist named Max Planck, Planck's constant. That's the relationship between the energy and the frequency. So now we're in a position, actually, to come back to the climate problem, kind of surprisingly. So let's think about the temperature of the Earth. So what determines the temperature of the Earth? In sort of the simplest picture, physicists like to talk about a spherical cow model, a model where we just ignore all the details and just try to get at the essence of things. Well, the Earth is illuminated by the sun. So the sunlight comes in. Let's say there's 6 units of sunlight from the sun. About 2 of them are immediately reflected off of the Earth. That's called the albedo. It's especially off of the clouds because they're white in the ice. This is the reason why we can see the full disk of the moon when it's near a new moon phase. It's illuminated by the light from the Earth. But the other 4 units are absorbed by the Earth, warming it. And then the Earth emits infrared radiation back out into space. And it's this balance between the incoming radiation and the outgoing that we're going to exploit to understand the temperature of the Earth. So the incoming radiation can be measured. It's the reason why, for instance, solar panels work, or why, of course, the Earth is warm or the trees grow. It's 1,361 watts per meter squared. Really a lot of energy coming in, face on in the sun. hitting that could be tapped for electricity, for instance. Now, what about the outgoing heat? So we can use quantum mechanics to find a little formula that says that the amount of heat that's emitted by the Earth varies as the temperature to the fourth power. So that means if we were to double the temperature of the Earth, the amount of energy going out would increase by 2 to the fourth power, 2 times 2 times 2 times 2, or 16. And this constant here, this number, which I'm not giving you the details of, that's where Planck's constant is buried. That's where the quantum mechanics is. This formula is a quantum mechanical formula. And we're going to make use of it to figure out the temperature of the Earth. So what we're going to do is we're going to balance the outgoing heat from the Earth with the incoming solar radiation, S. That was the 1,366 watts per meter squared. We're going to account for the fact that only 70% is absorbed. A was 30%, 0.3. That was the part that was reflected out into space. And then there's a factor of a quarter because the whole Earth is not illuminated directly by the sun. For example, half of it is in the nighttime at any given time, and half is in the day. And furthermore, even in the daytime, the sun doesn't directly fall straight down in most places. So it turns out there's a factor of a quarter. So we plug in the numbers, and out comes the temperature. And the temperature, according to this formula, is about minus 20 degrees Celsius. So it's a bit cold from this formula. From the point of view of plants, living things, this would be a problem. Everything would be frozen. But it's well below zero, well below freezing. Water would be frozen. But measured from absolute zero, we didn't do so bad. It's actually a pretty good estimate of the temperature. And this failure is a very instructive failure, because often in science, failures are more interesting than successes. The fact that we get too low of a number tells us that we need to look a little bit more closely at this problem. Now, it's often said that in understanding the climate of the Earth, there's only one experiment because the Earth, there's just one Earth. But really, there are many experiments that we can appeal to. And in particular, we can learn a lot by looking at our sister planets, the neighboring planets, Venus and Mars. Venus is completely covered with clouds. It's visible in the early morning hours right now. Mars, you'll be able to see as soon as you go outside tonight after the lecture. It's up high, and it has very little atmosphere. So let's see how things stack up when we apply this calculation to these so-called terrestrial planets. They're terrestrial planets because they're sort of Earth-like, at least compared to planets like Jupiter. So there's Earth. Our calculated temperature now in Fahrenheit is about 0 degrees, but the actual average temperature of the Earth is about 60 degrees. It's warmer in the equatorial areas. It's colder in the poles. But you average it day and night and so on. You get about 60 degrees. If we look at Mars, our formula says, well, the temperature should be about minus 70 degrees Fahrenheit. That's because Mars is further from the sun than the Earth, so it gets less radiation. We plug it in, and that's the temperature we get. The actual temperature of Mars is something like minus 63 degrees Fahrenheit. So we have a pretty good agreement. It's only 6 degrees off instead of 59 degrees off for the Earth. And that's because Mars has very little in the way of an atmosphere. An astronaut on the surface of Mars would have to wear a pressure suit to protect herself from the low pressure. If we look at Venus, surprisingly, our calculated temperature is lower than the Earth. And the reason for that is that Venus reflects 75% of the light that hits it. Even though it's closer to the sun, it reflects so much light that, according to our simple formula, it would be colder, all else being equal. But actually, of course, all else isn't equal. The actual temperature of the surface of Venus is something like 800 degrees Fahrenheit. It's even warmer. It's even hotter than Mercury, which is yet closer to the sun. So the difference between these two, we're off by a huge amount. And the reason for this is that the atmosphere of Venus is about 100 times thicker than that of Earth, and it's almost entirely composed of carbon dioxide. So we're going to need to think about the constituent atmospheres of the planets in order to do better. So let's look at some of the molecules that are in play. Especially in Earth, water vapor is very important. And the thing that is important about water vapor as far as climate is concerned is that the two hydrogen atoms that combine with oxygen to give us H2O have charge. The hydrogen has a positive charge, the oxygen has a negative charge. And so that means that this molecule will absorb and emit radiation very efficiently. Radiation, like infrared radiation, is an electromagnetic field, and it makes these charges move, and it can make the molecule start to vibrate or rotate and absorb energy and then re-radiate energy. So in particular, some infrared photons coming up from the surface of the Earth might be absorbed by this molecule and then re-emitted back down to the Earth, warming the Earth, accounting for that discrepancy of 59 degrees from our naive formula. Carbon dioxide has charges. Here's the central carbon, two oxygens. So it also responds to electromagnetic radiation, absorbs and emits it. The main constituents of the atmosphere are oxygen and nitrogen. Because we have either two oxygens or two nitrogens, they don't have any net charge. Each atom is the same as the other, so there's no place really for the charge to go. And so these things are transparent, and they don't play a big role in the emission or absorption of radiation. Now, if we look at an image of the Earth taken from space, from a satellite, looking in the infrared at one of the water wave bands, one of the frequencies from our Planck formula that corresponds to water absorption and emission, then I defy you, looking at that image, to tell me what continents this satellite is sitting over. You can't even see them, because what we're seeing is the surface of the atmosphere. We're seeing the atmosphere, the moisture in the atmosphere, maybe up to 5 kilometers, and it's completely obscuring the continents and the oceans underneath. So these might look like clouds, but what this is just water vapor being swept along by the westerly winds in the mid-latitudes. And then down here, you can see this movie was taken in October 2007. This kind of pulsing is the buildup of thunderstorms in the tropics during the day, and then they die off. You can see the sense of the trade winds blowing from east to west. So it gives a beautiful view of the atmosphere dynamics. And I'm going to come back to that in a little bit. So we can now we're in a position to improve our very simple estimate of the Earth's temperature. This is a view of the Astronomical Observatory on top of one of the big mountains in Hawaii. It's nearly 5 kilometers up, 14,000 feet up. And this observatory here has a telescope that looks at infrared objects. It can see beyond the visible. It looks at heat from distant objects. And the reason it's up here is because it's above the water vapor that would absorb that infrared radiation. And you can see that because the distant islands here we have these low clouds in between where all the moisture is. All the moisture is down below her. All the water molecules tend to stay closer to the surface. And it turns out that at about 5 kilometers, that's the point where there's no longer enough moisture in the atmosphere to intercept those infrared photons. And so an observatory built up here can see these objects. So how does that help us? Well, we can calculate what the temperature of the Earth is now to a pretty good approximation using this knowledge, because we'll start from our temperature that we found before. That's going to be the temperature no longer of the surface of the Earth, but 5 kilometers up, where the photons, the infrared photons, can escape out into space. That's where our simple estimate holds. Now, you probably know that if you go up in altitude, the air gets cooler, because basically molecules that are moving around, as they climb up through gravity, they lose their energy, their kinetic energy, and that's the same as temperature. And that works out on average in the Earth's atmosphere to about 12 degrees Fahrenheit per kilometer. So if we want to find the temperature of the surface, we start at 0 degrees temperature up at the top here, and then we increase by 12 degrees Fahrenheit per kilometer over 5 kilometers as we get down to the bottom. And there's our 60 degrees. We had 59 degrees, 60 degrees. That's going to be good enough for us tonight. We can get an estimate for the Earth's temperature. We can claim some understanding of why it is that the average temperature of the Earth is 60. Now, I'm sure a number of you take long airplane flights occasionally, maybe to Europe, and you may have been seated in one of those seats where you can monitor the temperature outside. And to me, it's always striking when the plane is up at high altitude that temperature is invariably minus 60 degrees Celsius. So I'm going to tell you why that is now. So when we're up above 5 kilometers, the atmosphere is very thin. And it's heated only by radiation coming up from the Earth. It's not heated by anything coming down from space because the sunlight just passes through that thin air. And there's no infrared radiation up at high space. So it's only heated from below and not from above. That's different than when we're down here at sea level, where there's radiation coming from the ground up to warm the air and also from the upper layers of the air coming down. So in our formula, we have to reduce the amount of radiation, the amount of energy, by a factor of 2. But you remember the radiation went like the temperature to the 4th power. Temperature times temperature times temperature times temperature. So in the rarefied atmosphere up in the stratosphere, we need to reduce our temperature by 2 to the 1/4 power, the 4th root of 2. We plug in the numbers, out comes minus 60 Celsius, in very good agreement with what you'll find when you're taking those long airplane flights and you're up around 38,000 feet. You're up near the stratosphere, the temperature is at the lowest point that the atmosphere reaches. So this theory, even this very simple theory, the spherical cow theory, based on quantum mechanics, gives us a deep understanding of the temperature of our planet and actually the temperature of many other planets. Okay, so there's one other thing we can do from this, which is, of course, as we all know, the concentration of carbon dioxide is increasing in the atmosphere. Here's the famous Keeling curve from Charles Keeling down at UCSD. That he started measuring in 1958 in Hawaii and Antarctica. It's been oscillating. There's the carbon dioxide concentration in parts per million. If he had been measuring 100 years previously, it would have been about 275 parts per million. But it's been going up and up. It oscillates every year. This is the seasonal cycle from the plants absorbing carbon dioxide during the spring and then giving it up when the leaves fall off and rot in the fall. Although this ended around 2009, we've now exceeded 400 parts per million. Sometime in the middle of this century, we will be at twice the level of the carbon dioxide concentration before the Industrial Revolution started. And we can use these simple ideas to get an estimate of the change in the temperature of the Earth. This is called climate sensitivity. So as I said, carbon dioxide will double sometime this century to 550 parts per million. And that will have the effect of raising the height at which these photons can escape to space from about 5 kilometers to 5.15 kilometers, by about 150 meters. It's not very much, but we can plug that into our little formula and figure out what the temperature increase would be. So remember, the air warms by 12 degrees per kilometer as we're descending. So if we're up an additional 150 meters, multiply that by 12 degrees Fahrenheit per kilometer times 0.15 kilometers, 150 meters, gives us about 1.8 degrees Fahrenheit or 1 degree Celsius of warming. Now, if that were all there was to the story, we wouldn't be so worried, I think, about global warming. But the fact is that this is amplified to some range of perhaps 2 to 3 degrees, and we can see easily enough how that might happen. One is that the water vapor, which is the most important absorber of infrared radiation, will increase. As the Earth warms, more water vapor will go up into the atmosphere. That's why the tropics are so much wetter than, say, the high latitudes. There's so much more humidity. And that water will then further increase this level of 150 meters up and lead to additional warming. Now, there's a lot of uncertainty exactly how much this will increase, but the estimates have changed very little over the past 4 decades at least. So here's a plot of a reconstruction of the temperature of the northern hemisphere of the Earth from AD 1000, over 1,000 years ago, up to basically the present. This comes from one of these IPCC reports, now over 10 years old, but it really hasn't changed much. And we see maybe some hint of an increase at this point. The projections show that this kind of range of temperature increase by the year 2100. So a little bit less than 90 years from now. There's some range of uncertainty here, but it's in this range that I was discussing from 2 to 3 degrees, especially if we go a little bit back further where we cross the doubling of carbon dioxide concentration. So that's the kind of warming that we're talking about. So what are the actual observations? This is a plot of the temperature of the northern and southern hemispheres of the Earth, not just the whole Earth, but separated into the northern and southern hemispheres. You see the southern hemisphere and the northern hemisphere have been warming. The southern hemisphere somewhat less than the northern hemisphere. I'm going to come back to that in a moment. But there's apparently a trend of warming consistent with our simple theory. Now, I'd like to come back at this point to John Muir, because often we hear a lot of skepticism about this theory of warming of climate change. But I hope I've given you a sense that it lies on rather firm ground, because our theory gives us an understanding of the temperature of the planets, gives us an understanding of the temperature of our stratosphere, why the Earth is the temperature it is, and so on. Most climate scientists, the vast majority of climate scientists, would say that that theory is in very good shape. So I want to return to John Muir. So John Muir never completed college, and yet he, on the basis of observations, realized that most of the features, the surface features in Yosemite, here seen from the top of Half Dome, this is Yosemite Valley, were due to the action of glaciers from the ice ages, the glaciers carving the rock. So what did the most eminent authority of geology have to say about John Muir? So he was no one other than Professor Whitney, whose mountain is at the terminus of the John Muir Trail. Professor Whitney, who was at Harvard at the peak of his career and chief of the California Geological Survey, said, "Muir is an ignoramus and a mere sheep herder," because that's how John Muir made his living initially in California, was by herding sheep, until he realized how much destruction they were causing in the Sierras. So I think that this is a very instructive example, because it shows that science, that the correct ideas win out. Here we have Muir, who doesn't even have a college education, but correctly realizes that glaciers are the main action, the main source of the shaping of the surface features of the Sierra Nevada, up against the eminent authority, Whitney, with all these credentials, head of the California Geological Survey, making fun of him. And yet, we now know that Muir was mainly right and Whitney was mainly wrong. There's a little bit of truth in, Whitney thought that the Yosemite Valley was caused by cataclysmic upheavals of the mountains. And there's a little bit of truth in that, and there are some faults in here that maybe weaken the rock, allow the glaciers to go. So often when one scientific theory replaces another, there's some remnant of the old theory. So I think that there's this idea that, well, there's scientists are suppressing dissident views about climate change, and that these dissident views wouldn't get a fair hearing. But I think this example shows that the correct views will win out. So now I want to move from this global picture of the Earth's temperature to some more controversial areas that we don't understand nearly as well as the one that I first outlined, which involved really two areas of quantum mechanics, the radiation given off by warm bodies and the radiation absorbed and emitted by molecules. We're going to see another place where quantum mechanics might come in. So the atmosphere is a quite interesting and complicated thing. There's a lot of things going on, winds blowing in different directions. A lot of this is due to the fact that most of the solar radiation is absorbed at low latitudes in the tropics, where it's warmer and cooler up here. So this causes the winds to move around and circulate, and causes the storms to move and so on. Something has been happening to that picture, though. So if we look at the extent of Arctic sea ice, so here's the Arctic Ocean, and this is the minimum amount of Arctic sea ice in September 1984. If we compare that to, say, September 2012, there has been a dramatic change. And we can ask the question, well, since there's been such a change and the Arctic has been warming, the temperature is been increasing up here more rapidly than other parts of the Earth, partly because of the exposure of the dark ocean waters here, allowing for more absorption of sunlight, warming it. Could that be changing the ocean circulation? So an interesting hypothesis has been put forward that perhaps some of the unusual events of, for instance, the last winter could be explained by the fact that the Arctic is warming, and so that the temperature difference between the lower latitudes and the higher latitudes is being reduced. The Earth is becoming, there's less of a contrast between the low latitudes and the high latitudes, the high northern latitudes. Down in Antarctica, things haven't changed nearly as much because there's such a massive block of ice down there, for one reason. Climate scientist Francis at Rutgers University has put forward this interesting hypothesis that perhaps the polar vortex that we heard so much about during the last winter, which may be responsible for the drought out here in the west, and also the persistent cold that we had in Rhode Island and other parts of the east, may be influenced, may be exacerbated by these changes in the temperature profile between the high latitudes and the low latitudes. This has gotten quite a bit of press. There's a lot of skepticism about this point of view, and there's a lot of active work thinking about this. So I think we'll bring this up as an example of science at work. We're seeing a hypothesis put forward, and then it being tested. There's pushback from a lot of very smart people trying to see, is this really a reasonable hypothesis? So for those of you who own Macintosh computers, I want to give you a homework assignment. So you can download a app that I've written for free called GCM, and you can run it on your Mac, and you can do a little experiment for yourself and see whether the Francis hypothesis is reasonable. Now, I should say this model is quite simple, so it's not going to give you a definitive answer, but it might give you some flavor. And in fact, when I did this little experiment, I was surprised by the outcome. I'm not going to tell you what the outcome is, but I'll let you, those of you who can do this, give it a try. So you can pick a model here. Let's pick a model that's sort of Earth-like. And one of these columns here, this temperature, 90 degrees, that's where we're putting in the temperature difference between the equator and the pole. And you could change that. You could make it 60 degrees to see if that would be a kind of model for the Francis hypothesis. And you can then run this model. And on a modern Mac, it might only take maybe 10 or 20 minutes for it to start doing something rather interesting. I'll let it run for a bit here. So it's starting what we're seeing is a kind of visualization of the winds. It's going to do something we call spin up. The winds are beginning to flow due to the effects of radiation. Now we're beginning to see at the high latitudes these alternating regions that are essentially high and low pressure regions. They're basically the weather fronts that we're used to. And if we look at the velocity of let's look at instead actually at the kinetic energy here. We'll start to see evidence of the jet stream. So we have this kind of meandering pattern, which is the jet stream of this model, and is a kind of simplified model of the jet stream that Francis is talking about in her hypothesis. So you can play around with this and try adjusting that temperature and see what happens. See if it really begins to meander more or not. Okay. All right, now, the reason I'm here, and a number of scientists are here, is that the KITP is having a program right now which is called Wave Flow Interaction in Geophysics, Climate, Astrophysics, and Plasma. And it's basically, the topic of this program is closely related to the problem that I just mentioned, where we have some flow of air, for instance, such as the jet stream moving around the Earth, and then we have waves superimposed on top of it, the jet stream perhaps meandering back and forth. And what a number of us realized is that this problem is common in a number of other areas, such as plasma physics, astrophysics, climate physics, as I talked about, geophysics. It probably appears in many different contexts. And the idea is to bring together these scientists to see if we can share ideas and perhaps get new insights into the questions such as this Francis hypothesis. So the KITP is a really wonderful place for us to be. There's increasingly few places where scientists can gather and think about these pure problems without the distractions of everyday life, and also dive deeply into them and not be worried about pressures from, say, governments to produce simulations or concrete results, to really get into the essentials, which is what physics is all about. And so I'm very happy that the KITP has given us this opportunity to have our program, which is now in its final week. We've been here for 13 weeks, I think, now. Now, I can't leave you without mentioning a few of the other systems. I've been spending a lot of time talking about the atmosphere, but there are a number of other wonderful fluid systems. And this is a visualization of the ocean looking at the surface currents. And you can see the dates here. So this is a reconstruction from observation and modeling. Here we see the jet stream passing, not the jet stream, the Gulf Stream. And we have these wonderful vortices, especially off of Africa, spinning off. Isn't that wonderful? So there's this tension between some structure, some simplicity, some order, and disorder. We have the order of the currents that are flowing around the boundaries of continents, and then the disorder of the waves. Here we have a nice wave. and the vorticity oscillating in the ocean. So the ocean is a particularly striking example of some of the ideas that we've been talking about in our program. Now I'd like to come back to one final example of where quantum physics may be playing a role, and that is we notice that quantum physics is statistical. We don't know where any one of these photons is going to land. All we know is that there are some places where they're more likely to land and some places where they're less likely to land. That was what bothered Einstein so much. He said, God doesn't play dice with the universe. Why is there this inherent randomness? And yet it seems so. So all we can say is that when we look at a lot of these photons, more of them are going to come here and less over here. So it strikes me that there's some similarity between this and climate. Climate is the statistics of weather. And as you all know, we aren't very good at predicting the weather very far in advance. Weather seems quite random. And so there's this great quote, climate is what we expect, weather is what we get. So what we expect is, based on probabilities, but weather, we don't know what the weather is going to be like in 2 weeks. We don't know whether the June gloom will return or not, for instance. So a number of us are asking, can we use tools and ideas borrowed from quantum physics and statistical physics to reformulate the question of climate? Can we get a deeper understanding of climate by importing these ideas that have been developed in other contexts in physics into climate science? Now, this isn't the first program that's been held here on climate change. In 2008, there was a very broad program on climate. And one of the interesting things that happened in this program is we brought together physicists and fire ecologists. And this was particularly apt because the year before there had been this huge fire, I'm sure many of you know, the Zaca fire, that burned over a large portion of the Los Padres National Forest. So a group of us took a field trip into this burned over area. And right here in this room, we held a conference bringing together all of these different scientists and different viewpoints, which led to an influential paper that published in Science, a survey called Fire in the Earth System. And the reason I mention this is that this work was recently cited in the new climate change impacts, the U.S. National Climate Assessment that just came out. There's a chapter there on fire, wildfire, and how it may be changing as the climate changes. So this is a very nice example, I think, of the KITP catalyzing this kind of deeper understanding of the climate system. One area that I hope that we'll be able to address here at some point is cloud physics. So clouds are very important and extremely complicated, but it seems that maybe a physicist could offer some important insights into thinking about clouds. Here's a view of the stratocumulus clouds, the June gloom from Camino Cielo, taken a month ago. And these clouds are actually one of the most challenging clouds to describe in climate modeling because they're low, they're very warm, and they radiate out into space. And because they're solid, bright, they also reflect a lot of light. So these clouds have a cooling effect on the climate. And the question is, how will they change as the climate changes? There's a lot of structure in these clouds. You can just see from the shapes of the clouds that the structure isn't going to be captured by a comprehensive model of the climate. One of these giant computer models will never capture all of this fine structure. So can we develop some physics-based understanding that could advance our ability to predict the behavior of these clouds? So there was a very nice experiment or comparison done recently showing how crucial clouds are. this is a comparison of 4 different climate models. They make different assumptions about the clouds and the atmosphere. And this was looking at the response that these models predict when the world warms by 4 degrees. And so this is the change in how much the clouds affect the radiation, the light, and the heat going between the Earth and space. And you can see how wildly different these models, the different predictions these models give, mainly because of the different assumptions that are made in modeling the clouds. And the precipitation pattern is very different. So in this case, for example, this is we'd have wetter, more precipitation right along the equator and less away from it. This gives the opposite prediction. So in fact, these differences between the models are more important, it turns out, than some of the other things that have been included in these comprehensive models, like vegetation, for instance. Just getting the clouds right would go a long way to improving our understanding of climate. And this is one of the major areas of uncertainty. So I'm just about finished. I'll leave you with this slide that appeared. This was a mural that appeared in the Rhode Island School of Design Museum a number of years ago. And it's an imagining of the Brooklyn Bridge in New York City, maybe 1,000 or 2,000 years in the future. The West Antarctic ice sheet perhaps has collapsed. Greenland has a lot of ice in Greenland has melted, and also the other ice in Antarctica has melted, so that the water level's up here. I think this is certainly in the back of our minds as we contemplate the climate problem, even though this is still in the distant future. It's something to think about. So thank you very much.
Thanks, Brad. That was great. I have like 1,000 questions, so I imagine there must be about 100,000 questions out there. So I only ask that you wait for the microphone from either myself or Kevin, who will circulate around so we can capture your question and the answer, because we're recording everything. Okay, so questions.
Is there any effect from the heating effect of the nuclear core in the Earth? I'd understood that threw off Lord Kelvin years ago in determining the age of the Earth.
Right. So indeed, the center of the Earth is very hot, but there are many intervening layers of rock between them, and so the conductivity of heat going through is quite small. So that in terms of the numbers that I discussed in terms of radiation, solar constant, it's like 10,000 times smaller. So we can ignore that for planet Earth. But for other planets, we can't. For example, Jupiter has even more heat coming out from the interior than it has coming down from the outside. So for Earth, we're pretty safe ignoring that, though.
What is your impression that I've read in some recent papers about the tilt of the Earth with respect to what you've just said? Is that important, or is it really not important?
Well, so it's certainly important in the seasonal cycle. So just because the Earth is tilted, its axis is tilted relative to the plane in which it travels. It gives us the seasons. And it's important for any detailed climate model to take into account that, for example, right now the northern hemisphere is receiving much more sunlight than the southern hemisphere. So it's quantitatively important. But something that's particularly interesting about that, I have a slide here, I think. When we go back and think about the ice ages, then the tilt, the changes in the tilt of the Earth's axis has changed over time due to the interaction with the other planets. And so the changes in the Earth's orbital parameters are the leading explanation for the cause of the ice ages, the things that carved, for example, the Sierras. So, so that's a very interesting area of investigation right now.
Doesn't have any bearing, or does it have a bearing on the whole aspect of climate change right now, as being reported in the newspapers and so forth?
Well, the tilt isn't changing over human timescale, so it changes very slowly, but it has to be taken into account in any detailed model of climate, and so in that sense, it's important. But it's not of overriding importance compared to some of the things that I've emphasized.
You attributed the feedback to carbon dioxide to increased water vapor in the atmosphere. My reading of literature is that in recent years, work by Susan Solomon, for example, has shown that the water vapor concentration in the upper atmosphere have not increased, and that's given as one reason for the current pause in temperature increases. Do you have a comment on that?
Well, I think so. There are many feedbacks, some positive and some negative. So I've only listed a few of them. And in terms of interpreting the recent past, that we're always on shaky grounds doing that, because the climate has natural fluctuations from year to year, or even over somewhat longer periods of time. So I wouldn't, as far as the so-called pause in the warming that may be happening right now, I wouldn't place a lot of stock in that. I expect that will change soon, and that the warming will continue. But monitoring the amount of moisture in the atmosphere is certainly a good thing to do, and that's a very important variable in following how the climate continues to change.
On a more immediate level, everyone here is conscious of the California drought, and there's discussion of El Nino. I know there's been a little of these issues raised in your program. Do you want to state anything on along these lines, or prospects, or thinking?
Well, I think that some caution is necessary, because California has had droughts in the past, such as in the 70s and earlier. And so in interpreting the present-day drought in terms of climate change, one always has to take into account that fact that especially in the West, there have been long periods of drought associated with the natural variability of the climate system. Now, that doesn't mean that climate change won't exacerbate that. And indeed, that seems to be suggested by some of the models. But it's when we try to get to more specific predictions of certain regions, then we encounter some of these uncertainties that I've discussed, that I've emphasized in the end of my talk.
In quantum physics, you generally deal with probability amplitudes and then calculate probability. And
right.
Earth is a classical system, so you're dealing with probabilities. How does that?
Okay, so right, we're not saying in using the mathematics of quantum mechanics, we're not saying that the Earth fluid or the climate system is quantum mechanical per se. Quantum mechanics is playing a role in these components, such as the radiation, as I've discussed. But this idea of using the mathematics to reformulate the climate problem is, it's by analogy, basically. So we're not saying the Earth is quantum mechanical in some fundamental way, but just using the technology of that.
How much of a role do the Krakatoa easterlies play in your models? Or are they just too high?
So from an explosion, from a volcanic explosion, are you talking about? Or okay. So volcanoes, large volcanoes, can inject a lot of dust up into the upper atmosphere and cause a temporary cooling of the Earth. And that can be simulated in models and then matched against experiments. So that can be an interesting way of testing models. And that's been done. My model, the one I showed, is far too simple for such a thing, but that's been done by the more sophisticated models.
Well, I mean, but the Krakatoa easteries are there all the time, whether there's a volcanic explosion or not. And I wonder, do they play a major part in the scheme of things?
Okay, I don't know specifically about Krakatoa easterlies. There's certainly easterly winds in the low latitudes, so maybe that's what you're thinking about, and those are certainly important. Yeah. Hi.
I'm wondering, because as you said, you were showing a very oversimplified model of the atmosphere, and your atmosphere and your stratosphere was in 5 kilometers when it's actually the middle of the atmosphere and not the stratosphere. And then you mentioned something about that the impact would be in this theoretical atmosphere in 150 meters about. And I'm wondering, what is the implication of using or the real atmosphere in your quantic vision?
Okay. One thing I forgot to emphasize is that 5 kilometers isn't to be thought of as the beginning of the stratosphere. That's still well in the troposphere. That's the place basically where most of the water vapor no longer will be above that 5 kilometers. So the stratosphere is more like 12 kilometers up. Now, it's true that I gave you a very simplified discussion, which has the advantage that we can understand it without a computer. But this kind of simplified model is informed by the more comprehensive and accurate, presumably accurate computer models. On the other hand, we wouldn't really have faith in the computer models, or we would be very skeptical if it disagreed or we couldn't give an interpretation of them in terms of these simple ideas. So it's because we have this kind of simple understanding that we have some confidence in the computer models. And I think that fact is underemphasized in some of the discussion about those complicated models. With the complicated models, certainly, they're the most complicated models that human beings have created. They have millions of lines of computer code and big teams working on them. And they're a very active area of research with many open questions, some of which have been discussed in our program. Yeah. I think.
Is there a satellite that's providing... You have to wait for a microphone to go down.
Just a moment, please.
Hi, thank you for the work you do. I, many years back, saw a very interesting program on PBS on NOVA that was addressing the switching of the poles and the magnetic north. And in that program, they had created similar models. And one of their predictions was drastic climate change. And I wondered if that's being addressed in the physicist community.
Right, so the reversal of the magnetic field of the Earth is due to internal currents inside the Earth, from the flow inside the Earth, where the magnetic field lines are connected. And that's occurred many times in the geological past. I'm not very familiar with this area. I think people have looked for some climate signal at the transitions, and I'm not aware of any strong signal, but I could be misinformed about that. But that's talking about a much longer time scale than the one that I'm talking about.
Yes, I have been curious for a long time about how the temperature of the Earth can be represented by a single number when we have such variation from pole to pole and all of this. And I've never seen a clear explanation about how this temperature is arrived at. Could you enlighten me and enlighten the audience as to exactly how they arrive at this temperature and what does it mean?
Right. That's a very good question. So one thing we can do is we can simply average the temperature measured at many points over the surface of the Earth, trying to weight the different areas of the Earth equally and get a single number. But then you can ask, well, what does that mean? And it is a very convenient abstraction because it allows us to reduce some of the uncertainties in our models. The models have uncertainties due to the flow of heat between different regions of the Earth. But if it flows out of one region and into another, the average will tend to cancel that out and will tend to reduce those uncertainties. So it gives us a way of looking for a clear signal. But in terms of human beings or what we experience, it's kind of a useless number, to tell the truth. Just the fact that the Earth is warming by a few degrees, what does that really mean? What we really want to know is how much is Santa Barbara going to warm, how much will the rain drop by, and so on. So those are the things that really matter.
Is there an error bar associated with this estimate of temperature?
Absolutely.
Plus or minus what?
Well, so you can see from the observations that it fluctuates a lot from year to year. So you would have to say, well, when are we asking what is the average temperature of the Earth? What year? And then there are error bars, which aren't shown on this plot, but actually they were shown over here in this longer time extrapolation. This faint gray area. This gives you some sense of the year-to-year fluctuation plus errors due to the reconstruction of the temperature. In this case, when we're in the distant past, we're looking at the scientists who created this are looking at tree rings and ice cores and all sorts of different ways of trying to get the temperature. There's errors associated with that, and so that's a big area of discussion. You notice when we're in the modern era here, the error is less because there are actual thermometers, but thermometers themselves have measurement error, and there's a large amount of discussion about that point. So it's a very complicated question, really, that I've kind of compressed. Actually, every slide here could be an entire semester course. So that's how much compression I've given you tonight.
Is there a satellite or a series of satellites that's providing an accurate measurement of Earth's surface temperature?
There are quite a few satellites that are measuring the temperature of the Earth and various properties of the Earth. Any measurement system has limitations. So satellites, they're trying to get the temperature of the Earth by looking through the layers of the atmosphere, and that is an imperfect art to do, to figure out the temperature at different points. So what's really needed is a combination of satellites plus ground-based measurements, plus measurements from balloons, planes, as many different sources as we can find from ships, from ocean buoys. Also, all these different sources of information each have their own limitations, need to be combined together to give a best estimate of the temperature.
Is the measurement of microwave radiation an accurate judge of temperature?
So the Earth, at the Earth temperature, most of the emission is not in the microwave. It's in the infrared. And so that is where you would be looking for the temperature signal. There's some microwave emissions, but I'm not aware of that being used right now. Maybe it is, but I'm not aware of it.
Yeah, hello. I wonder if you could comment a little bit on the practice of this science. I'm thinking about finding out how did Yosemite Valley form, or how does the June gloom behave. And I wonder if you could maybe compare and contrast a top-down approach of finding things out or a bottom-up, Mm-hmm. So we can say that Yosemite formed by some sort of massive polishing and carving, or we can start from more basic principles and say that there was a time when ice formed, and okay, what does ice do? Similar thing with the clouds. You start with modeling the behavior of particles and find out, oh, in the aggregate, it behaves this way. Or do you take a look at it and say, oh, it's white and shiny.
Right.
And I wonder if you can compare and contrast, or if you find it like a chicken and egg thing or a complementary thing.
I think the answer is you have to do both. You have to try to start from the ground up, from the small to the big, and from the big to the small. So Muir actually was sometimes criticized for only looking at the big things and ignoring the small things. But a lot can be learned by looking at exfoliating granite and maybe the crystals, and looking at little defects where water is seeping in and cracking and so on. So it's the combination that really can advance the understanding. Similarly with clouds, we could go all the way down to the molecular scale. We could look at aerosol particles and the formation of droplets. So that's called cloud microphysics. And you can try to work back out towards the climate models, but that's a long ways to go, from nanometers to 1,000 kilometers. Or you can try to start from the big scales and work down. So I think in dealing with these complicated systems, there's no one right way. There's a myriad of different approaches, and then hopefully you can meet somewhere in the middle.
Thank you.
You mentioned the jet stream in some of your slides. Apparently that's just a narrow ribbon speeding around the Earth a few hundred kilometers an hour. It's 200 kilometers wide, 10 kilometers thick. It's a very odd thing. Is there any simple physical way to see that such a thing should exist at all?
So that's something that we talk about quite a bit in our program. So one can get a general understanding of the westerly flow of the atmosphere just by thinking about the temperature difference between the equator and the pole. So that leads to pressure differences, which in combination with the rotation of the Earth, the Coriolis force, leads to a flow of the atmosphere from the west to the east. But to get the details, that by itself would suggest a very broad flow. To get the details of why we can get very narrow jets is a very interesting question, and it has to do with the interaction between waves and mean flows. The waves, they're called Rossby waves, transporting angular momentum, and how that can sustain a rather narrow jet. So that's actually quite an interesting scientific question. And it's very different, it seems, on, say, Jupiter. The jets there seem to be very different than on Earth, or compared to the oceans. The ocean jets are quite different from the atmospheric jets. So that's an area, I think, where some fruitful progress is being made, and more can be expected.
Yes. My question is, we all agree that the Earth is warming. Is that correct?
No. There's always somebody who disagrees. So, but many people agree. Most scientists, most climate scientists agree that the Earth is warming right now.
Okay. We all agree that there's a variety of variables that are causing this, correct?
Well, maybe. So I've outlined what I think are some important variables.
Okay. To what extent, in your personal opinion, is mankind's current lifestyle, this industrial revolutional lifestyle, to what extent is that contributing not causing, but contributing in your opinion?
So I stand with the majority of climate scientists in thinking that our emission of carbon dioxide, our changing of the atmosphere, is leading to observable changes in the climate in the present day. So I think that's quite well grounded in physical principles, as I've tried to outline tonight. But we can have many disagreements about, and we do have many disagreements about the detailed implications of that.
Okay. Do you believe, though, that it's causing an acceleration, and can that be demonstrated?
An acceleration in what?
In the warming.
I don't know if there's an acceleration of the warming, but it seems that there's warming. Warming is increasing.
The pictures you showed of the receding of the glacier were pretty dramatic, but the warming of the Earth, according to your slide, is only 1 degree over the last century. Is that, in your opinion, enough to account for the loss of the glacier, or is there another factor?
Oh, yeah, okay. So, the glaciers are complicated. So it's not just temperature. It also has to do with precipitation. So the glaciers tend to accumulate at high altitudes where you get snow, and then they're melting below. So changes in precipitation could be playing an important role, and do play an important role in glaciers. In the case of the Lyell Glacier, it's also possible that agriculture in the Central Valley has deposited some dust particles on the surface of the ice, making it darker so that it absorbs more heat. And probably a combination of these factors are playing a role in that particular glacier, and in fact, many glaciers around the world. So glaciers by themselves, taken in isolation, can lead to a rather complicated story. Yet their disappearance in most places, but not all places in the world, is quite striking.
I have a question. There is this phrase called the butterfly effect.
Yes.
Maybe you've heard of it. And the idea there, I guess, is that a butterfly flapping its wings in Texas could eventually cause a typhoon in southeastern Asia, something like that.
Yes.
Is that something you believe really happens in our climate system?
Well, one can. So it's not possible, of course, to run the Earth with and without the butterfly.
All the computing power you wanted.
Well, you don't even need all the computing power. You can run a climate model with and without a little perturbation. Maybe not as small as a butterfly, but you can ding it a little bit. Maybe one of the measurement stations went offline. And then you can follow how that model, it's the same computer running the same model, how it diverges over time. And that's the reason why we can't expect to be able to predict the weather more than a few weeks in advance. Because if we ding it a little bit, we know that the effect will blow up. It can blow up and lead to qualitatively different results. So, but we're used to that in physics. And in fact, the gas in this room is behaving much the same way. The detailed trajectory of each of the oxygen nitrogen molecules depends in some complicated way on if I move my hand a little bit, an hour later, that molecule over there is doing something different. And yet, we still have an understanding of the gas here. So there is the possibility of understanding even with that kind of sensitivity.
But maybe not as small as a butterfly, you're saying.
Yeah, well.
you won't chime in on the question of whether a butterfly could cause a hurricane.
Well, by extrapolation, it seems quite possible.
Volcanic emissions, sulfur dioxide, and are they a tiny part of this whole picture? Or?
Well, so volcanoes, occasionally we have very large volcanoes, like Mount Pinatubo in the Philippines that blew up in the early 90s. It spewed a whole bunch of stuff up into the atmosphere, causing a temporary cooling of the Earth. But that stuff rains out after a couple years. So it causes some cooling. And possibly in the geologically distant past, there have been periods of time with large amounts of volcanic emissions that could have led to severe climate change. But in the present day, these are kind of little spikes, little perturbations every now and then, which can't be predicted really by climate models, of course, but they might provide useful information into how the climate is responding.
Hey.
Hi.
Yeah, so most of the maps I've seen of warming show more warming at the poles than at the equator. And so essentially, I guess maybe the standard deviation of the temperature would possibly be shrinking, you know, the difference between that.
That's right.
And what implications does that have for things like the jet stream or other things like that?
So that's the Francis hypothesis. So it's striking that there's this, it's called polar amplification, causing the reduction of the temperature difference between the low latitudes and the North Pole, not the South Pole, but the North Pole. And so one might suppose that could have some effect on the circulation on, for example, the jet stream. One reason to think that that might not be the case is that that polar region is relatively small. And so it may not be so important in the climate system, even though it's very striking that the sea ice has decreased so much, and it's very visually apparent. Its actual effect on the global circulation may be small, and that's what a number of scientists who are questioning this hypothesis have said. So.
I have heard allegations that the solar wind and cosmic rays play a role in a climate. Is this small, or is this something that should be considered?
I think it's definitely something that should be considered. The Earth is subjected to cosmic rays raining down, and these charged particles may, for example, cause clouds to, may form cloud condensation nuclei, places for cloud droplets to form. There's been some experiments studying them. I'd say there's no really strong evidence for this, but it's something that we should keep an open mind to. And so sometimes there's some weak evidence for the climate varying with the solar cycle, the 11-year cycle, 22-year cycle of the sun, which has some influence on the cosmic radiation that hits the Earth. But it always seems to be a very weak signal. And but there might be some surprises. Yeah.
I think we have time for one more question, if there is a... Well, I have got 999 left, so I'll ask one more. The plot you showed of the temperature going back 1,000 years or more, that's the hockey stick diagram or something?
Yeah, more or less, yeah.
It looks very constant for hundreds of years, but I've read somewhere that in the age of the dinosaurs, like in the Permian period, temperatures were higher than today. So that's... Obviously, you can't extrapolate that back millions of years.
Right.
So what are the causes in your mind for the rises in the past of carbon dioxide, presumably, that raised the temperature then?
Okay, well, so as we go further back in the past, our understanding certainly gets weaker and weaker. So if we go back not 1,000 years, but 10,000 years or 100,000 years, we're dealing with the ice ages. And even there, our understanding is pretty incomplete. There's the timing is probably set by the astronomical changes in the Earth's orbit, but there's a complicated story with the carbon dioxide concentration in the atmosphere changing in sync with the temperature, and how that actually happens is not really understood. And then if we go back millions of years, then the continents are beginning to be different, mountains are different, processes that might be changing carbon dioxide on those long time scales and other gases are different. So then it's a rich story, and it's, I think we've only touched the surface. But I do want to take the opportunity with that question to address one point, which is that often we hear the idea that, well, the climate changes in cycles, and so we're just going through some cycle right now. But if you think about this time scale here, I mean, how many generations ago was 1,000 AD 1,000? That's like 50 human generations ago. So we really don't have any real comprehension of what that kind of time scale is. And that's only halfway back to the Roman Empire. But that's 50 generations, and we only retain a memory of a few generations. So when we see this kind of oscillation, we have to keep in mind that we're talking about, from a human point of view, a gigantic period of time. And then, of course, going back to 1 million or 1 billion years, the problem is just, we can write that down in terms of numbers, but we don't have any real understanding in terms of our own existence, I think.
Brad, for a great talk.
Thank you.
And there are some food items out in the common area.